but I want you to have a better understanding. So I'm going to take all the stuff that we did for like 5 or 6 days and boil it down to 10 minutes. I'm gonna put it all in one place and tell you what everything is and why that piece is there, and explain to you all the little nuances I want you to know. And we're not gonna do any examples. It's gonna remind you of all of these things. So, and I have some little pictures and stuff I'm gonna pull in here. I'm just picking 2 objects. I want to be really clear. It doesn't matter what these objects are. It just needs to be 2 objects that have mass. So the first thing I want to remind you about is if you have any 2 objects with mass, they will experience a mutual force of attraction. That force is governed by Newton's law of universal gravitation. This is the force that pulls the 2 objects together. You guys ask me questions often that I answer in class, so if you're writing notes, maybe the first thing to do here is to remind yourself that the force pulls both objects together. It's based on the mass of each object, and I've used this word a lot, the separation distance between the centers of the 2 objects. There's different R's, and so we only have one letter. I can make it uppercase or lowercase, but we use the same letter to represent many things. So you have to be careful about, what R means. I purposely use different R's in different equations to make you think of it, because they do mean different things. You have to decide what that R means. Now, if I just have 2 objects in space near each other, as I do right here, and there's nothing else happening, then the 2 objects are going to be pulled towards each other. Now, I would assume the smaller object will be pulled more than the bigger object, right? We know this because net force equals MA. They both experience the same size force, but the one with the smaller mass will have the larger acceleration. So if we're talking about a rocket and a planet, the planet's not going to accelerate hardly at all. The rocket is going to accelerate a lot. Now, this part's the first thing we talked about. The acceleration due to gravity is the result of connecting these 2 things together. We could determine the acceleration due to gravity on the rocket by setting this equal to m1a. This would tell us the acceleration of gravity on the rocket. Now, that doesn't mean very much if we're talking about the rocket being way far out in space. But we did talk about how the acceleration due to gravity near the surface of a planet could also be figured out this way. Generally, to do this, the R becomes the radius of the planet, since that's the effective separation distance. So if you wanted to find G for a different planet, you place your object right there at the surface and you calculate the acceleration that way. This will give you the acceleration near the surface of the planet. But I need to impress upon you that there's still an acceleration here. There's acceleration everywhere in space between any 2 objects. It's just that it's not necessarily very effective. I mean, if you put something out where the moon is and it doesn't have a velocity, it will fall towards the Earth. It'll experience an acceleration. It won't be 9.8 meters per second squared because it's further away. It'll be less. This is why we say that the astronauts aren't weightless. They appear to be floating because their spaceship is falling at the same time. But they're accelerating downwards the whole time. It's just that they keep moving and they move out of the way of the planet. And that's where we started. Any questions about that? Now, if I, for just a moment, ignore the acceleration part and talk just about force. The rocket is just going to fall to the Earth if nothing else is happening. Meaning if I just have this rocket out in space, it's going to experience a downwards force. That force will get larger and larger and larger as it gets closer to the planet, because as it gets closer to the planet, R is going to be getting smaller and smaller and smaller. So that force changes as it gets closer. If the rocket has a velocity, any kind of velocity, it doesn't have to be anything special. If it has any kind of velocity, it may fall and not strike the Earth. This could create an orbit. It doesn't have to be a circular orbit. It can be any kind of orbit, and sometimes these orbits are kind of weird. They don't have to be perfectly nice. They can do all sorts of weird things. There are lots of unstable orbits out there. If it doesn't have enough velocity and it starts here, it'll just fall into the planet. This is how you bring something back to Earth that was in orbit. You slow it down and let it crash into the Earth. You try to control that as much as possible to make sure that as it crashes into the Earth, it hits the atmosphere and it lets the atmosphere maybe slow it down in a manner that doesn't destroy the spacecraft. That hasn't always been successful. Sometimes we let things just burn up in the atmosphere. But for the most part, if you're trying to bring humans back and you would like them to live through the process, you try to make sure that when they come back to the planet, they maybe hit the atmosphere and they slow down over the course of a longer time so that they don't, experience too much acceleration and die because of that, or have the spacecraft burn up. There's been at least once where that was unsuccessful. So when the Columbia came in for its deorbit burn, unfortunately, its wing had been damaged. When it came through, it burned up. It was not able to slow down at the rate that it was supposed to. It tumbled haphazardly across most of the United States, raining debris around the entire United States until it finally fell into the fields around Texas and Mississippi and all sorts of places. But for the most part, when we try to deorbit something, we try to do so in a stable way. Or if we're just throwing something away, we try to deorbit it and have it fall into like an ocean somewhere. Not that that's great either, it's just throwing our trash away someplace else. But the whole point is, all you have to do is slow something down and it will fall towards the planet. A stable orbit of any type is one in which it's moving at such a rate that it does not strike the planet. There are lots of stable orbits. The one we talked about being able to calculate was a circular orbit. Now, circular orbits are very particular. Most orbits aren't circular. For there to be a circular orbit, we want to have an orbit such that the object is experiencing centripetal acceleration. This was the next thing we introduced. A specific velocity that will allow your object to be in a circular orbit around the planet. Now, a circular orbit around the planet is not necessarily easy to do, nor is it going to be something that is particularly, what the word I want to use here is, most orbits aren't circular. Go. In a circular orbit, we are trying to make it just perfect. And when I say just perfect, we're trying to make a perfectly matched velocity that matches up with not just r, little r here, representing a radius of curvature, but also matches up with the separation distance in such a way that the force of gravity that acts this way provides a perfect centripetal acceleration. This is a whole lot of things that have to be in perfect balance. First, that velocity is very select. There's just one of them at every different orbit. It's a very select velocity. It has to have this kind of balance, meaning there has to be this particular amount of velocity and radius to give you this particular centripetal acceleration. And that particular centripetal acceleration has to match up with the amount of force you have at that orbit. That's a whole lot of things that have to be just right. Now, we can find out what that velocity is, but that velocity is different for different radiuses of curvature. So here's what we decide. Is the radius of curvature the same as the separation distance? For an object that is very big, then yes, the radius of curvature and the separation distance will be the same. But if the object that's doing the orbiting is big compared to the object that's being orbited, those two things aren't the same. So we have to look at that, and that's the question you have to ask. Is the object that's being orbited much bigger than the object doing the orbiting? If it is, then those two r's are the same. Notice, and this is important, that the object that is orbiting, the small thing, its mass doesn't matter. It cancels out in this relationship, which tells me that all objects that are at the same orbital location must have the same velocity no matter their size. Now, yesterday I ran into some math problems with folks, but we can multiply both sides by r here, correct? If we do that, it cancels one of the r's here and both of the r's there. Now, this should tell you something very clear. How fast you go depends on how far away you are. The further away you are, the slower you go. It's that simple. So if you want to be in a circular orbit, the further away you get away from the planet, the slower your object has to be traveling. That's all that really says. So now we have several things to put together. I'm going to write them over here because we're going to have some extra stuff in just a minute. So again, this is the thing that pulls them all together. This can cause an acceleration that can happen on both objects. If we want an object to be in a circular orbit, we can do so by making sure that we have just the right velocity at just the right orbital distance. And when we put those things together, we find out that there is a relationship between the orbital speed and how far away from the object we are. So all those things together. Now, at the same time, there are other parameters that we often use to describe orbits. I can think of three orbital parameters. First, there's your orbital velocity. This is constant for a circular orbit only. For any other orbit, it's not going to be constant. It's going to change all the time. Orbital radius is a word I used. So you could be asked, what is the orbital radius? We also talked about altitude. And why is that different? Well, because that's the height above the surface of the planet. That's the altitude. We should know the difference here. This would be the orbital radius minus the radius of the planet. Thus the difference in definition. Yesterday, me giving you the radius of the planet, many of you took that to mean that was r, but it wasn't. And then there's one more thing, and that was the idea that we could, instead of talking about the velocity, we could ask another question. We could talk about how long it takes to orbit. But how long it takes to orbit is based on how fast you're going and the radius. That's what makes that challenging. And that's what made yesterday's question hard. I asked you to find the altitude, which means you needed to find the orbital radius. What made that extra challenging was the fact that, well, the orbital radius determines what the speed is. And because it determines what the speed is, and the speed determines how long it takes, all of those things are interconnected. So I said if you wanted to use what I gave you, which was the period yesterday, you had to combine these two things together. That's how you're able to find the radius. And we can do that as well. It gives you just a different function. If I combine those two things together, I get m2g over r on this side and 2 pi r over t squared on that side. Now, there's no good or bad way to solve this. It just relates two things together. You'll get m2g times t squared equals 4 pi squared r cubed. This relates the period to the orbital radius. It's a consequence of all of these things together. Again, you can solve for any of these on your own. These are considered your basic functions. These are first principles. Newton's second law, Newton's law for universal gravitation, and the definition of centripetal acceleration. These are considered fundamental principles. Or first principles. If you're asked to derive something, you have to start from there. These are consequences of putting those things together. They're just consequences. This isn't really a first principle. This is just distance over time. Not really a first principle. Just a definition of velocity. Those were all the things you needed for yesterday. And then on top of it all, you had to hit the buttons right. And let's face it, for some of you, hitting the buttons right isn't great either. Not to mention that I saw some weird algebra out there. Weird algebra. So those are all the little things. So when would I use the radius of a planet? Let's answer that question. I can think of 2 times, maybe 3. Case 1, you would use it if you were finding the acceleration of gravity. Near the surface. That'd be the first time. That's where I'm saying, if we want to know what the acceleration of gravity is near the surface of a planet, then we say, all right, we're going to drop somebody near the surface of a planet. We're going to effectively say the separation distance is the radius of the planet because they're near the surface. And we'll do net force equals ma, where that will be mass of person, mass of planet. No, person and planet's bad, so how about mass of human, mass of planet, g over radius of planet squared equals mass of human times g. This would be a way to find the acceleration of gravity near the surface of a planet. The second time you would use the radius of the planet is if you had a low planetary orbit where you were effectively orbiting the planet somewhere very close, maybe even inside its atmosphere. Something like that. So our object is very close to the surface of the planet. In fact, that was the first orbit we talked about, which might have been a problem because here, basically, if you're just outside the atmosphere, the radius of the planet might as well be your orbital radius because the difference, the altitude, is very, very small. You would also use the radius of the planet, though, if you're trying to find an altitude of an orbit that is clearly not at the orbital radius. So if I'm trying to orbit from, say, here, it's clearly big enough to not be the radius of the planet. But if I want the altitude, I'm going to need the radius of the planet because the altitude is that distance above it. I think those are 3 times we're going to need the radius of a planet. Any other time, that's Mr. Shelton trying to distract you. Okay? Yes, sir?
Would you ever kind of get the opposite of the last question where like you get outside of the radius and then you just get separations?
Sure. There's no reason not to. All right. Anything else? Again, based on what we just talked about, I have 3 objects in orbit. I want you to put them in order from fastest to slowest and put an equal sign between any that are the same. Now, hopefully, if done correctly, you realize that A equals B. That should be the first thing we did. Those objects are at the same separation distance. And all I'm using is what we solved for a minute ago. If R is the same for both of them, then V has to be the same for both of them. But these both have to be greater than C. Right? R is twice as big for C as it is for A. So that means it's going to have to be smaller. It's further away. And the fact that this object is bigger than this object doesn't matter because the only mass that matters is the mass of the object being orbited. All good there? All right. I want to talk about elliptical orbits a little bit more than we talked about yesterday. I have 2 different orbits here. I have one orbiting at a distance r and another orbit that is 3r. And I have the spaceship that's in an elliptical orbit between the 2. All right? So here's the spaceship when it's all the way far away, and here's the spaceship when it's very close. It's in an elliptical orbit. Yesterday I told you should know when the spaceship is traveling at its fastest and when the spaceship is traveling at its slowest, and the names of what those spots are. Do you have those in your notes yesterday, or did we get that far in this class? All right, well, let's talk about those places. First, this is where the spaceship is the furthest. We call this apogee. That's the furthest away. This other one we call perigee. It's closest. That also means you didn't get a couple of other vocabulary words I would like you to have. Like, the red line there is the semi-minor axis. And the blue line there is the semi-major axis. So I'll say those again. The blue line, semi-major, and the red line, semi-minor. These won't be on a test necessarily. What might be is that eccentricity is how elliptical your orbit is. And it's the ratio of the minor to the major axis. The smaller that ratio is, the more squished out your ellipse is. In fact, an eccentricity of 1 is a circle, because those would be the same if it was a circle. Okay? So the Earth has like an eccentricity of 0.97 or something like that. It's very circular. But you start getting further away from the sun and the planets have more elliptical orbits. But none of them are terribly elliptical. Now those are just names, and I do want you to know the vocabulary. But what I really want you to understand is what's happening to an object that's in an elliptical orbit. So I'm going to get those things out of the way, or try to. There. And focus just on the orbit itself. When you're at apogee, your velocity is too small to be in a circular orbit. So you'll notice it falls below that circular line. If it had a fast enough velocity, it would travel in this circle. But it's just a little bit too slow, so it falls below the circle. Right? It's too slow for it to be a circular orbit. Now, while it's falling, gravity's still pulling on it. I mean, right from here, gravity's pulling this way on the spacecraft. And so when the spacecraft makes it to here, it's going to start speeding up and going faster, because part of the pull of gravity is causing it to turn its path, but part of the pull of gravity is causing it to speed up. This is what's different about a circular orbit, where the circular orbit, the force of gravity just causes it to change direction. In an elliptical orbit, the force of gravity is speeding it up and changing its direction. It's too slow to be in a circle here, but by the time it makes it all the way to here, now it's going too fast to be in the smaller circular orbit. And so it's going to basically overshoot the circular orbit that's here. It's just going too fast, so you'll notice it will transition outside of a circular orbit. Of course, it's as close to the sun as it's going to get. So on its trip back, say when it makes it to here, it's going to have a velocity in this direction, but the sun is pulling on it this way. So on its way back out towards apogee, the sun is still changing its direction, but it's slowing it down. So an object in an elliptical orbit does not have a constant velocity. It has a minimum velocity when it's furthest away and a maximum velocity when it's closest. So an object in an elliptical orbit spends less time close to the planet and more time far away from the planet. Now, it's important to understand this, that the planet or the star, whatever it is, isn't located at the center of the orbit. It's located at a special place called the focus. Ellipses have two foci, focuses, foci. They have two foci. The planet will be at one of them. The other one will just be empty space. Now, a circle is when the two foci overlap and are in the same location. Now, you guys who are in pre-calc, you'll go through how to find the focus of an ellipse. It's not fun, but you'll get to do it. You'll do focus of parabolas, ellipses, hyperbolas. Have you guys done that yet in pre-calc? Oh, just you wait. There's lots of formulas for all of those things, and I don't remember any of them. But sure, it'll be a blast. No, it won't. No, it won't. You'll do all this stuff. I've told you the things I want you to know. Maximum velocity here, minimum velocity here, and now you're transitioning between them. It's falling beneath the outer circular orbit and going too fast for the inner circular orbit. Now, here's the thing. When the rocket is here, if it wanted to suddenly be in the circular orbit, it would have to speed up, right? The actual circular orbit here, the centripetal orbit required, is faster than the minimum. So if the rocket hit its engines there, it would change its orbit to be the outer circle. Similarly, if the rocket slowed down here, then if it suddenly slowed down, it could be in the inner orbit. It's going too fast for the circular orbit, and when it's at perigee, if it suddenly slowed down, it could transition to that inner orbit. This is how you get to the space station. You don't go directly to it. The first thing that happens is that the space capsule goes out to a lower Earth orbit. They make sure the space capsule isn't in danger and has nothing that will endanger the space station. Then they've timed it so that the space station is going to pass overhead but is traveling slower because it's at a higher orbit. And then the capsule fires its engines to go into an elliptical orbit to meet up with the space station. That's what this is. So you imagine the space station is traveling slower. It's out here. And the spacecraft is going to come out and try and catch up to it. And that's how they transition from one orbit to the next. They do the same thing when they deorbit. They detach a spacecraft, allow it to go to a lower orbit, check it out, make sure it's doing okay so it can withstand the pressures coming back into the planet, and then they deorbit it all the way. So orbitary transitions and translations like this is what they're doing out there in space. Just hitting the engines for a brief second to change their speeds to go from one orbit to the next. I want you to be able to say those things in a written response. That if you're at a lower orbit, you have to be at the perigee of that orbit in order to go out to a higher orbit. You want to change from a circular orbit to an elliptical. So right here, you would suddenly increase your speed. That would put you into an elliptical orbit with a higher apogee. You got to the apogee, and you have to speed up out there to get up to the speed for that. So I'm trying to get you to do, I'm not going to tell you all the details, because that would take me forever to talk about all of them. I'm saying that when you're at perigee here, you're already going too fast for the circular orbit. You're going to transition to a higher orbit. When you're there, you're too slow for a circular orbit. So if you want to go to a circular orbit here, you're going to have to speed up. If you want to go to a circular orbit down here, you're going to have to slow down. Just a side note, they try to do this at apogee and perigee. The mathematics is easier, but they have a very short window to do so. So they have to do it really fast, fire the engines quickly to do a sudden change of speed at either one of those locations. Otherwise, they're traveling at some angle over here, and it becomes more difficult to do the calculations, even with computers.